A-level physics, going through topic by topic. We're going to start having a look at gravity, gravitational fields. What is gravitational strength? So let's go and step in and have a look at what is gravity. Now, we all know about the story here about Sir Isaac Newton. Sitting under a tree, supposedly reading a book, and the apple comes down and falls on his head. Never happened, of course, but much more likely that he was actually watching somebody else and he saw an apple fall, and it gave him some sort of thoughts and ideas about, why is it happening? So we've got a simple question, what is gravity? Gravity is something we just take for granted. It's obvious that, if we have something, it's going to fall. If I do a simple experiment and I hold the rubber up here and I let go, it falls. It crashes to the ground. And we have various problems with understanding things about gravity. I find my students still have a real problem when I take two objects. I'll just grab two, a USB and a battery. One's heavy, one's light, but I let go of them and they hit the ground at the same time. So I can repeat it as many times as I like, but they still hit the ground at the same time, because gravity's nothing to do with the mass of an object, although it does seem to have something to do with that. So this is perhaps some sort of force of attraction. Gravity's a little bit odd, because when we look at most things in science, we find that there is for every positive a negative. I find we've got something like an electron, and I find there's an opposite. I find there is a anti-electron, a positron. We find we've got things like a proton, and we've got its antimatter equivalent, the antiproton. We've got all sorts of things. They're always in pairs, but we come with gravity and this is paired with, well, who knows? We can call it anti-gravity, I suppose. But what is it? A force of repulsion? If we could have anti-gravity, we could do all sorts of things. All the science fiction writers would be happy that we could then make gravity and have spaceships where we can walk in the spaceship and like we've got gravity, because their budgets probably don't allow for everyone to have zero gravity to try and do anything. And even zero gravity is really a sort of something that doesn't really make sense, because let's suppose I move up a little bit. So let's have our picture of the Earth, and I'm just gonna, alright, I was gonna grab a template of this and I'm failing miserably. Yep, failed miserably. Here's my Earth, found one. Right, so if you're standing on the surface of the Earth, yep, gravity is pulling you down. But let's suppose you're in my favourite country, Australia, where everyone sort of lives upside down. And again, they're just pulled in by gravity. They're not upside down, of course. They are, as we know, the right way up. It's because gravity pulls down regardless of what we're trying to do. So there is no sort of hanging on if you're down in Australia. But what happens if we move up a little bit? So let's take this person and let's have them fly in their aeroplane. And for those of you who've flown in an aeroplane, for those who've ever stood up in the aeroplane and tried to go to the loo perhaps, you'll discover that we've still got gravity. But if I can put you up just perhaps something like, I don't know, 150 miles up, and I put you in sort of a little space station, then everyone says up here they're weightless. People confuse things. They say there is no gravity. And of course, that's wrong. So, gravity doesn't disappear. It just, other things might become bigger or more important than gravity. So, what is this gravitational force? What is a gravitational field? What's this thing that keeps satellites in orbit? So, if we were to take a look at the Earth and the Moon, let's just draw these out. So we'll take a picture here of the Earth, and we won't draw it to scale, but we'll shove out here the Moon. What people don't seem to realise is that, you know, the Moon is actually quite a long way away, and it's still held by the force of gravity onto the point of where it is, which is sort of the centre of the Earth, and that's where it's being applied and pulled into. So we can calculate things like this gravitational force. Now, what is this gravitational force? So we can say that the force between two objects, F, is going to be related to something called the gravitational constant, and the mass of one planet, the mass of the other planet, and that's divided by their distance, which is the distance between their centres of mass squared. So this is one of Newton's ideas when he came about looking at gravity. But I want to be more specific than gravity is a force of attraction. We've got to remember that gravity is a force of not attraction, but of mutual attraction. So just as one thing attracts, then so does the other one. So a mutual attraction. All objects with a mass they simply have gravity. So all objects with a mass have a gravitational force, and the size of this force well, what does it depend on? It depends on 1, their masses, and 2, their distance. The larger the masses, then the greater the force of gravity, and the larger the distance, the less the force of gravity. Gravitational forces are typically weak forces. And if I look at 2 particular objects, here we are, my rubber and my pencil, they have a force of attraction between them. But we don't notice this, and we don't notice this because there's such a much larger gravitational force around us that basically we don't notice what this one is, because the Earth is so big compared with the pencil or the rubber that it becomes insignificant, and the force of gravitational attraction starts bringing other things so they sort of move in together and clump together. And that's basically how a star works. A star works by gravitational attraction starting to pull things together. And a star, of course, works by fusion, and that works because the elements are pulled in really tightly and closely together. And then, of course, you get a nuclear reaction which throws them apart, and gravity pulls them back in together again. And a star is simply a battle of throwing out and pulling in, and it's in balance. One thing we learn very rapidly with gravity and many other different things is that gravity follows something called the inverse square law. So this simply means that if I've got one distance, whatever that could be, that's going to equal one force of gravity, whatever that is. If I double the distance, then we'll only get a quarter of the gravity. If I go 3 times the distance, we'll have a 1/9 of the gravity. And if I go something like 10 times the distance, I would have 1/100 of the gravity. So let's have a look at a simple example. And my simple example is very easy. We've got something like the Earth, and I've got something like the Moon quite close by, and we're measuring these from the center of gravity to the, again, center of mass or center of gravity on the other one. Okay, so what can we work out about this? Well, there's a fair number of things we can work out. Let's try and see what we can do. So the Moon orbits the Earth with a radius here of about 3.84 times 10 to the 8 meters. We can have here the mass of the moon, and I know someone probably popped it on a pair of scales and they measured it as 7.35 times 10 to the 22 kilograms. It wasn't there when they did it, but the mass of the Earth was also probably measured, and that comes out at about 6 times 10 to the 24 kilograms. Newton sat down, he worked out the gravitational constant, G, capital G, and that's 6.67 times 10 to the minus 11 newtons per meter squared per kilogram. So gravity 6.67 times 10 to the minus 11 Newton meter squared per kilogram. It's a very small number, and that tells us that gravitational forces are very small, unless of course you're looking at a whopping great big mass like the Earth. Right, so the gravitational force here of attraction keeps the Earth, I might as well give it a name, and the Moon connected. There's attraction between them, and let's have a look at what that size of that force is going to be. So we'll start off with F equals capital G. We've got the mass of the Moon and we've got the mass of the Earth, all divided by the radius squared. This gives me 6.67 times 10 to the minus 11 times the mass of the Moon, 7.35 times 10 to the 22, times the mass of the Earth, which is 6 times 10 to the 24, and that all is going to be divided by my radius, which is 3.84 times 10 to the 8 all squared. No other way, but we need to go and plug this into the calculator. So let's start with our little equation, and our gravity is going to be 6.67 times 10 to the minus 11. That's going to be multiplied by the mass of the Moon, 7.35 times 10 to the 22, multiplied by the mass of the Earth, 6 times 10 to the 24, and all that's going to be divided by 3.84 times 10 to the 8. That was sad, I didn't look at that. Oh, there we are, bracket, 3.84 times 10 to the 8 all squared. Let's have a look, and out pops our number 1.99 times 10 to the 20, and our units here are going to be newtons. So that is our force That's the force of attraction between the Earth and the Moon, which keeps the Moon in orbit. Now let's suppose we're going to fire a rocket, and I'm going to fire a rocket to the Moon. Always fancy doing this. So if I've got a rocket going to the Moon, well, we need to know the mass of the rocket. I think we can make up the mass of a rocket, and let's give this in some sort of kilograms, and we'll call this one 5 times 10 to the, what should we go, about 10 to the 5, something like that. And I want to work out what its gravitational strength of the Earth will be on this rocket as it comes up. It orbits, and then off we go. So at that point, and we want to work out what it's going to be at that point from the Earth. So let's choose a distance. Well, that's 3.84 times 10 to the 8. So let's imagine we're going to try and work it out when it's just 2. So I'm going to set my radius here to be equal 2 times 10 to the 8 meters. One of the times when I did this, I did it quite nicely and managed to actually have the rocket inside the Earth, which is always a little problem. We should be alright on this one. Right, so let's see if we can work out what is, first of all, the gravity here between the rocket and the Earth. So between the rocket and the Earth, then we've got my same formula. Force is G. This is going to be the mass of the rocket and the mass of the Earth over the radius squared. So this is going to give me 6.67 times 10 to the minus 11 times the mass of the rocket, which is going, as I said, was going to be 5 times 10 to the 5 kilograms, times the mass of the Earth, which is 6.0 times 10 to the 24, and we're going to divide that by the distance to the Moon, which in this case I said was going to be 2 times 10 to the 8 all squared. Well, we can go and put this one in to the calculator, and what I'm going to do here is I'm going to save a lot of effort, and what I'm going to do is I'm just going to save my effort by simply there deleting this. So that's going to be 2 times 10 to the 8, and the other one I'm going to work on is my mass of my, instead of the Moon there, we're going to have 5 times 10 to the, we had 5 times 10 to the 22. Let's take these two out, and this is only going to give us times 10 to the 5. And we've said our rocket is going to be 5. So we can work out here a number like here, 5,002 newtons. What's going to be the force on, that was the Earth. If we do this equation again, we can do gravity, the mass of the rocket. This time it's going to be the mass of the moon over the distance from the moon. Well, my distance from the moon, we can work out quite easily, was, if we had a radius of 3.84 times 10 to the 8 and I'm 2 away, that means I'm going to be 1.84 away from the moon. And we're looking at then this distance is going to be 6.67 times 10 to the minus 11 times, this time the mass of the rocket, 5 times 10 to the 5 times the mass of the moon, 7.35 times 10 to the 22. Let's put these into the calculator, and I only need to change this distance. So instead of being 2, we know this is going to be 1.84, and I can look at the other value, which was 6 times 10 to the 24, and we can see that this is now going to be 7.35 times 10 to the 22, and that's going to give me here a whopping great 72 newtons. At some point in the journey, when the rocket is at a certain point along here, because the Earth's got a larger gravitational force than the moon, then the net force on the rocket will actually be 0. The distances for the forces, if you want to try and work them out and balance them, the balance point is at about 3.45 times 10 to the 8 away from the Earth, which means that that point is pretty well about here. Which is a sort of a sobering thought, to think that you're virtually at the moon when the gravity of the moon cancels out the gravity of the Earth. Way it goes. So, gravitational fields. What are gravitational fields? Well, we said that a mass has a gravitational field, and very much like magnetism, we've got gravitational field lines. These are the lines of the gravitational field. So in a similar way we draw the magnetic field lines, so we can also have, I'll draw it around the other way, it'll be happier. We can have gravity pulling in all directions, but always towards the center of the Earth. Assuming you could go to the center of the Earth and it wouldn't be a little bit too warm for you, and assuming you could actually just get there, if you could actually stand at the center of the Earth, then you would find that it's the outside of the Earth which would be attracting you, and you would be effectively weightless. That's only because the forces balance one another. For spherical objects such as the Earth, the fields are radial, and all those field lines point towards the centre of the mass, the centre of the Earth. These field lines tell us two things. The arrows on them tell us about the direction of the field, that they're pulling towards the centre of the Earth, and the spacing of the lines should give us some idea of the strength of the field. And as we see, as we get further from the Earth, so the field lines become largely further apart and the field is weaker. When we're very close to the Earth's surface, there are going to be in fact some small variations in the gravitational field. I know that where I sit there seems to be this gravitational anomaly I've mentioned before. When students try and calculate gravity, and they do that by various things, the ball drop experiment or using a pendulum, whatever it might be, they find that here, just this little point here where I'm sitting, is a gravitational anomaly. The gravity is either up to the strength of something like Jupiter or barely that of the Moon. It's interesting how that varies from almost 1 second to the next. So we've got this thing called gravitational field strength. What is this gravitational field strength? Well, I'm going to call this G. And this is when you measure the strength of the Earth's gravitational field at any point using something like a mass on a spring balance. The stronger the field, the greater the gravitational force pulling it. So we can say the gravitational field strength, G, equals the force divided by the mass. Yeah, G equals F over M. Now I did actually write an A there because also it is the acceleration due to gravity, and this is about 9.81 newtons for every kilogram, and this is also the same value as the acceleration due to gravity, which is 9.81 meters per second squared. Now what we can do is we can join these two together. So I want to work out what little gravity is. Well, little gravity equals force over mass. And we've also got the other relationship where I know the force equals big G, the mass of one object, the mass of the other object, over r squared. If we then basically combine these with this F here, and I can substitute in there, we get then little gravity is big G over M over r squared. So the field strength G at any point around a mass m is going to be related to the distance it's measured from the centre of the mass. And we know this is another one of these inverse square relations, which we could see by looking at those field lines. So we know that as you get further away from the Earth, the field lines are spread over a larger area, and so the gravitational force comes down. Where does this become important? Well, it becomes important with things like satellites. So if we're playing around with satellites, then we've got to try and put up an artificial satellite into the Earth. There are usually some trick questions which come up. What's the first satellite? And that's the Moon. But I remember being told about Sputnik, our first satellite, our first artificial satellite coming into space. Now let's see what happens when we do this. So let's have our Earth, and what we're going to do is we're going to launch a satellite into space, but I don't launch it with enough effort and it hits us. If I launch it with enough effort, nothing's working nicely today, then what we can do is we can get it just enough so that it can fire up and it can enter orbit. And if we do that, then this will stay in orbit. If I fire it with a little bit too much vigour, and this is enough to get what we will call escape velocity, which is 11,200 meters per second, then it escapes gravity of the Earth altogether and carries off, as I watched the Mars probe do only a couple of weeks ago. So if I get something without enough velocity, it's going to fall back to the Earth. If we can get it into orbit, it's going to fall at the same rate that the Earth is moving. So the satellite is basically in what I would term free fall. And that's going to depend on its distance away for the orbit. So we can sort of get satellites to move at different speeds depending on what orbit we want. And if we can get enough, then this would move basically away from the Earth and carry on. Now, if I want to put something into orbit, I've got different types of orbit I need to worry about. So the types of orbit, one that most people know are the geostationary orbit. This basically means that it's going around the equator at somewhere around about 35,900 kilometers away from the Earth, and it will take exactly 24 hours to do one orbit. Another type of orbit we can get, which are often done by things like weather satellites, and satellites that are going to look at various bits of pieces over the Earth, is we can put them into a polar orbit. And this means simply that if I take my Earth, then the polar orbit is going to take this satellite over the North Pole and the South Pole. The Earth, of course, will rotate. This orbit stays the same, so that this satellite will now visit every place on Earth. And the other option is a low Earth orbit, such as the International Space Station, and this is basically going to move around the Earth at a different speed than the Earth is rotating. But it's going to go basically over the equator again. So I've got this, and in a low orbit it's going just to go round. So something like the ISS would be this. We can do all sorts of calculations to work out about these satellites, and let's have a look at one of these. We know that the gravitational force of attraction is going to equal the mass times the centripetal acceleration. So I know that G m1 m2 over r squared is going to equal the mass here times the velocity squared over r. Well, this mass 2 is in fact the mass, and so these can cancel out, and what we're left with, because we've already worked out what G is that little g equals v squared over r. So let's suppose we want to put some sort of spaceship in orbit. Can we then work out some equations for this? Yeah, we can work out various sort of things to work out about an orbit. We can work out something like the sun going round the Earth, but we're going to start with just a simple satellite going round one of these things. Oh yeah, planets. and see if we can work those out. Let's try one of these things. So I've got a spaceship and it's going to orbit the Earth, and we're going to think about some information about this. So let's try a geostationary one first. So let's look at a geostationary orbit. So what do we know about the orbit? Well, we know that it's going to be 35,900 kilometers above the Earth's surface. But I'm not interested in that. What I'm trying to work out is the distance from the center of the Earth. So that's going to be a larger figure, and we'll say it's going to be something like 4.23 times 10 to the 7, because I'm measuring from the center of the Earth as opposed to anywhere else. Well, what do we know? Well, I've got to work out the rotation, here, period, I'm going to call it T. It's going to equal 24 hours times 60 times 60, which is 86,400 seconds. It's a bit sad, but there are some numbers that I do know, and I've had to work out that one so often I can give you that one. Right, so we're going to assume it's going to be circular orbit. These things aren't always exactly like that, but we'll do that. So let's see if we can work out the speed of the satellite. So what do we know for the speed of the satellite? Well, I know the circumference is going to be 2 pi r, and the speed then of my satellite is going to equal the distance it travelled, which is the circumference, divided by the time, which is going to be that number of seconds. So my circumference is going to be 2 pi times this distance here, 4.23 times 10 to the 7, all divided by 86,400. Let's do a calculation here. So doing my calculation, it's going to be 2 times pi times 4.23 times 10 to the 7, all divided by my time, which is 86,400. And that gives me here some sort of speed here of about 3.076 times 10 to the 3 meters per second. Now let's cheat. Alexa, what is 3.076 times 10 to the 3?
The answer to your calculation is 3.076.
Well done. All right. Alexa, what is 3,000 meters per second?
Can you say that again?
I give in, really. Alexa.
Sorry.
Alexa, what is 3,000 meters per second in miles per hour?
3,000 meters per second is about 6,700 miles per hour.
There we are. 6,700 miles per hour. Which is faster than you go in your average car, I imagine. In fact, if you want to go to the moon, you've got to travel at, as I said before, about 11,200 meters per second. So if you want to know what that is in miles per hour, we'll try it. Alexa, what is 11,200 meters per second in miles per hour?
11,200 meters per second is about 25,100 miles per hour.
And when I watched, quite a few years ago, man walk on the moon for the first time, they also, those men, had gone faster and travelled faster than any other men before them. Well, not actually, because they went to the moon several times before that and they had a look, but they didn't land. So yeah, perhaps not the right statistic to give you, but the fastest men alive, those that travelled to the moon and back. Next time we're going to look at the work of a guy called Kepler, and what Kepler did is he started having a look at something really exciting, which was the orbits, because in those days it was believed that the world was still the centre of the universe, and people tend to get rather upset about him when he started suggesting and proving that the Earth wasn't, and it went round the sun, and all the planets fitted in with some really nice equations. And so we'll have a look at that next time. If you found this useful, then please like and subscribe, and I will see you next week when we do some more A-level physics, topic by topic. Until then, stay safe. Bye bye.